All right, general chemistry. I hope you're doing well this week, and it's good to see you again, or at least you can see me. I wish we could get together and be at the school again, and we could be working through this stuff live, but we just don't have that option right now. So I hope you're doing well. As always, email me questions if you have any as we go throughout the week. But this week, our focus is on understanding the pH scale and how that measures acidity or basicity of a solution. And then not only how does it measure it, but how does it relate to quantities that are actually in the solution. So we're going to look at, in this first video, different types of scales. And a scale is used, the most common application is just a weight scale. You have a little kid here being measured by a doctor, and maybe their weight comes out to 65 pounds. That scale measures weight. We might measure length on a scale called a measuring stick or a meter stick or a tape measure, and maybe we get a measurement of 115 inches. But what happens if we have a scale that has to be able to measure really, really large differences in numbers? So an extremely small item and a really large item, or something else like extremely small numbers and very large numbers. So something like this: what if we have to measure a red blood cell, and we also need the same scale that can measure all the way out to the size of the Earth, or maybe even the size of the solar system? Well, on a scale that large, it's going to be hard to differentiate between individual red blood cells. These might not all be the same size. And if our scale is so large to include a red blood cell and the solar system, it's going to be hard to pick out individuals' differences in the small things and individual differences in the large things, just because how large the scale is. So we're going to develop this idea of a logarithmic scale. And I want to do that by giving you basically a little analogy. So consider this. The case of the interesting paycheck. Let's say that you started work somewhere, and your boss said, I'm going to pay you $1 on the first day. And then every week, or the first week, you only get $1 for a week of work. And then the second week, I'm going to multiply your salary by 10. So $1, second week could be $10. Well, if we plot this and we continue this for a couple weeks, we're going to get this wide range of values on our scale here. So we're going to go up the scale here. So 1 and 10, if we graph that, we get something that looks like this. On the first week, we have $1, and the second week, we have 10, and we have this jump of a factor of 10. You can see the jump on our scale here. This is a difference in 10. Okay, well, the next week, we get $100 on our paycheck, and if we graph that, it looks something like this. Now, you can already see that because this next jump of 10, it squeezed our first jump of 10, so there's a smaller gap here. This is 1/10 of the total distance between our $10 and $100 paycheck. And it's starting to make these numbers here seem less of a difference, or less of a change here, even though this is still a factor of 10. Well, if we go on to our next week of pay, it's not even going to fit on my black line here. We need to squish our numbers together, our 10 and our 100. So let's shrink those down. And if I shrink my scale down, now I can fit another factor of 10. And on the next week, I get paid $1,000. If I graph that, it looks something like this. Well, if you continue that out, I'm going to squish the 1,000 down now. And you can see our numbers are getting smaller and smaller. These are getting closer and closer together. It's harder to differentiate now between the 1 and the 10. And we put the 10,000 on there, and we graph it. And again, you can see on our scale, it's harder to differentiate between these lower dots because they're so small in comparison to my 10,000 now. A 1 and a 10 is very small for that. If we continue that out for 10 weeks, our graph's going to look something like this. And you can really see it now on 10 weeks of pay. Our 10th week of pay, we're in thousands, millions, billions. We would get $1 billion for our paycheck. It'd be a good day. But if we look at our pay here, these first dots, they all look like they're zero. They're just kind of flatlined along the bottom. And because of our scale here, this is called a linear scale, we can only really differentiate between our last 2 or 3 weeks of pay. And then it just looks like we're just kind of at the bottom there. So how do I tell the difference between all these little numbers here on my graph? Well, it's really hard because we're using one scale, linear scale, to measure all these values. So how do we change that and make it look different? How do we make it so we can differentiate between all these dots in the red box down here? Well, we take this linear scale and we convert it into something called a logarithmic scale. Now, a logarithmic scale is a base 10 scale, and it allows us to look at changes over a really large scale or range of values, and we can still look at incremental changes at the small side or the large side of those. So this is how it works. It's pretty simple mathematically. So let's take our week 1 of pay is $1. And how do we get from our linear scale to our logarithmic scale? Well, you do a simple calculation called the log. And it's the log base 10. And if you're in a calculator, you can just find your log button, or if you're on your phone, you'll find the log button. And if you click it, it automatically defaults to log base 10 scale. and you put the number in parentheses and hit enter. And so if we do that, log of 1 in our calculator, hit enter, we get 0. If you're doing that in a calculator, you might have to type in the 10, or you might not. So the one on the left there says that you're log base 10. If it just has a log with parentheses, it's defaulting to be a log base 10 power. So if we do that for week 1, we get 0. If we do that for week 2, log of 10 equals 1. Put in your calculator, hit enter. And if we do that for the first 3 weeks, we get 0, 1, 2. Well, what does this actually mean? Let's look at the log of 100 here, equaling 2. What does a logarithmic scale do, and what does this log function in your calculator actually do mathematically? Well, log of 100 literally means 10 raised to what power, that's our question mark there, 10 raised to what power equals 100. So log base 10 is 10 raised to what power equals the number in the parentheses of your logarithm. Well, we know that 10 squared would equal 100, so that question mark can be filled in with the number 2. And 10 raised to what power equals 10? Well, the answer would be 2. And that's why the log of 100 is equal to 2, because it answers that question, 10 raised to what power equals 100. Normally, at this time in the school year, you would have done this in your math class. I don't know where you're at in your math class this year. If you haven't done log powers, this is what a logarithm is and how that scale works. So log of 100 would be equal to 2. Okay. Well, if we do that for 10, log of 10 means 10 raised to what power equals 10? Well, 10 raised to the first power equals 10. And that would be log of 10 equals 1. And you can do that for all of them. So we do that for week 1 through week 10. We get all these values. And if we jump all the way to week 10, we'd have the log of a billion. And log of a billion means 10 raised to what power equals 1 billion? Well, 10 to the 9th equals 1 billion. So log of 1 billion equals 9. And you could plug that in your calculator, check and see. Pretty simple math here. Just have your calculator do it for you. And you get an answer of 9. So the log scale ends up being 1, 2, 3, 4, 5, 6, 7, 8, all the way to 9 for each week of pay. Well, if I graph that, I can get a graph that shows differentiation all the way from the first week and second week to the last 2 weeks. So our linear scale, if we convert those into scientific notation, you might be able to see the relationship here as well. One could be scientific notation 1 times 10 to the 0 power. That's where that 0 comes from, logarithmic scale. Our $10 would be 1 times 10 to the first, 10 to the second, 10 to the third. And you can continue that all the way down for each week of pay and see where the log powers of 10 come from. But if we want to look at these two scales again, if we graph them, our first scale, the problem was that paycheck increased by factors of 10, and there's such a big difference for a range of values here on a linear scale that you only get to see the difference between the first 3 values. Well, if we do this in a log scale and I do the calculations and I get 0, 1, 2, 3, 4, all the way to 9, if I graph this on a log scale, each week my salary would change by a factor of 10, and it's going to be equal change on my log scale. So 4 to 5 would increase by a factor of 10, 5 to 6 would increase by a factor of 10, and any value of 1 on this scale, a difference of 1, would be a difference of 10 in my pay. And that's how log scale works. So now I can go all the way back to the beginning, and it's easy for me to see the first week and the second week has a difference of 10. The second week and the third week has a difference of 10. And the third week and the fourth week. And I can show that all the way through for all the weeks. You can't show that here. I don't see the factor of 10 here because that linear scale, I just squished all my values down to almost nothing. And so the log scale is great for measuring large ranges of values. You'll notice there's no units on here. We don't include units after we do the logarithm. So if you plug in a value in a logarithm, it drops its units afterwards. You just get a number after that. So where do we apply this? Maybe you've been watching coronavirus cases across the globe, but this would be one application. A lot of these scales will do logarithmic scales. So these are cases across the globe, starting in middle of January all the way till now, and this is just updated today. So we're over 3 million cases right now. And you'll see at the very beginning, it's hard to tell what happens to the number of cases because just this flat line compared to 3 million, we're barely moving on our graph right here. The dot, the size of the line here is larger than the number of cases that we have to start out. So I just chose one here, February 21st. Cases are 770,000. It's hard to tell when are we double 770,000 and when are we half of that, or when are we 10 times 770,000. If we turn this into a logarithmic scale, what happens is instead of being linear here, 0 to 3 million, we're going to have every mark on the scale, so let me go back here, every mark on this scale is a factor of 10 or a power of 10 change. We're going to do the same thing here. I'm going to turn this into a logarithmic scale. So we have 1,000, and then an equal distance between 1,000 and 10,000, and then an equal distance between 10,000 and 100,000. So if you did this as a log scale, log of 1,000 would be 3, log of 10,000 would be 4, log of 100,000 would be 5, and then 6, and then 7. So this would be our log scale. They just kept the actual numbers in there. And what does that do to our graph? Well, this flat line at the beginning where we can't tell any difference between all of our values, now we can tell a difference here. For 1,000, looks like our cases were mid-January or late January, we had 1,000. And to go to 10 times as many cases, we would go up to where we're at the 10,000 mark here. And we'd say late January, maybe a week to double or to multiply my cases by a factor of 10. And then to go from 10,000 to 100,000, looks like we're close to 100,000 here for February, right? Maybe at the very end of February. So it took about a month to go up another scale factor of 10. And now we're at 100,000 to a million. And you can compare those values, maybe early March to the beginning of April, so another month to go up by a factor of 10, and that's how log scale works. So we're at 3 million now here, so we're somewhere between 1 million and 10 million. And if you look at our scale here, the difference between the 1 million and the 10 million is a factor of 10, but if you actually added up all the numbers in between here, there's a lot more numbers between 10 million and 1 million than there are between 1,000 and 10,000, and that's how log scale works. It stretches that scale out, so you can see all of the differences all the way across the scale. So there's your introduction to log scales. Let me just go back to what we did here for our conversion between the two. The only thing you want to know is it's pretty simple math here. Don't let this scare you. All we do is take our number and we take the log of the number and we get it in a log scale. And that's how we measure log scale. So that'll help for the start of this unit, looking at the difference between logarithmic and linear scales. And our applications are for numbers that have really large ranges of values.